Okay, so for our next problem, problem number 4, so we have the integral of e to the negative x hyperbolic sine of 2x dx. So in this type of problem, so it's for this type of problem, so if since we have here an exponential function, then we need to express the hyperbolic function in terms of its exponential form. Okay, so this will become integral of e to the negative x. So uh, applying the equivalent exponential function of hyperbolic sine of 2x, so that is 1/2 times e to the negative e to the 2x minus e to the negative 2x, okay, dx. So since this is a numerical coefficient, so we can take it outside the integral sign and then distribute e to the negative x to the two terms inside the parenthesis. So we will have 1/2 integral of, so e to the negative x times e to the 2x. So the same base, all we need to do is add the exponent, so negative x plus 2x, so that's e to the x minus, so multiplying this, so e to the negative x multiplied by e to the negative 2x, so add the exponents, negative x plus negative 2x, so that's e to the negative 3x. Okay, so we can now distribute the integral sign and the 1/2 and the dx. So we will have 1/2 integral of e to the x dx minus 1/2 integral of e to the negative 3x dx. Okay, so let's recall that the integral of e to the u du is equal to e to the u plus c. So remember that the du should be the complete differential of u. So let's check. So here our u is x, so our complete differential is dx. Okay, check. However, in this one, so we have our u is negative 3x, therefore our du should be negative 3 dx. So therefore, so this will be 1/2 integral of e to the x dx. However, for the second term, so 1/2 integral of e to the negative 3x. So the complete differential of the exponent should be negative 3 dx. Okay, so since we added a negative 3 as the coefficient of dx, then outside the integral sign we will multiply its reciprocal, so times negative 1/3. Okay, so this will now become, so integral of integrating e to the x dx, so that is 1/2 e to the x, and then this will become plus 1/6, and then e to the negative 3x plus c. So second to the last example, so we have integral of dx over hyperbolic sine of x plus 2 hyperbolic cosine of x. So this problem is similar with number 4 in a way that we can only integrate this if we express the hyperbolic functions into their exponential forms. Okay, so let's express hyperbolic sine and hyperbolic cosine in terms of e, not the exponential function. So we have here integral of, okay, so integral of, so the hyperbolic sine, that is 1/2 e to the negative x, e to the x minus e to the negative x plus 2 multiplied by identity of hyperbolic cosine is 1/2, and then we have e to the x plus e to the negative x. Okay, so let's extend the vinculum. This is dx. Okay, so let's simplify that. So we will have since we have here a denominator of 2, no, so maybe we can add them directly. So we have integral of dx over e to the x minus e to the negative x over 2, right? Plus, so if we distribute this 2, this will become 2 e to the x plus 2e to the negative x, right, over 2. So adding, since we have the same denominator for the denominator here, so we have so adding, so we have a denominator of 2, so this will become e to the x minus e to the negative x plus 2e to the x plus 2e to the negative x. Okay, so since this is a complex fraction, so we will divide this, no? So in dividing, so it will become dx multiplied by the reciprocal of the denominator, so dx times 2 over this, so this will become integral of 2 dx over, so simplifying, so this will become 3, so 3e, yes, 3e to the power of x, and then add this, so this is plus e to the negative x. Okay, so to eliminate e to the negative x here, so we will multiply this with both the numerator and the denominator, multiply it with e to the x over e to the x. Okay, so we can take the numerical coefficients outside the integral sign, so this will become 2 integral of e to the x dx over over 3e, so multiply e to the x times e to the x, so it will become 3e raised to 2x. Okay, plus e to the negative x times e to the x, that will become 1. Okay, so it's not that obvious, but we can actually integrate this using inverse trigonometric functions. Okay, so this is actually 2 integral of e to the x over, so this is square root of 3 e raised to x squared, okay, plus 1 squared. So we can actually use arctangent now to solve this. Sorry, there's a dx in here. Okay, so we can use now the integrals that lead to inverse trigonometric functions, particularly the arctangent. So integral of du over a squared plus u squared is equal to arctan of u plus c. Okay, so here our u is square root of 3 e raised to x. So our du would be square root of 3, and then the differential of e raised to x is e raised to x, and then multiply by the differential of the exponent, so dx. Okay, and obviously our a here is 1. Okay, so as you can see, so the numerator should be du, no, for us to apply this formula. So du should be the numerator. So our du is square root of 3 e to the x dx, and here we only have e to the x dx. So therefore, we have a missing numerical coefficient of square root of 3. So therefore, we must write that, not to complete the differential. And then, since we have written square root of 3 in the numerator, so outside the integral sign in the denominator, so we will write square root of 3 to balance that. Okay, so we can now apply the formula. So it's in this form already. So we have 2 over square root of 3, and then this will become so there's a missing in the formula, no? So it's du integral of du over a squared plus u squared is equal to 1 over a arctan u over a plus c. Okay, sorry. So this will become 2 over square root of 3, and then the integral of this is 1 over 1 for a, and then arctan of u over a. So our u is square root of 3 e raised to the power of x over 1 plus c. Okay, so rewriting that, so we will have 2 over square root of 3 arctan of square root of 3 e raised to x plus c. Okay, so you can also rationalize this. So in rationalizing, so we have 2 over square root of 3 times square root of 3 over square root of 3, so that will become 2 square root of 3 over 3. So 2 square root of 3 over 3 arctan of square root of 3 e raised to x plus c. For our last problem, so we have this one. So show that the integral of dx over hyperbolic sine x is equal to ln of hyperbolic tangent of x over 2 plus c. Okay, so in this problem, we will be going to be using a lot of identities. So we have integral of dx over hyperbolic sine of x, so dx over hyperbolic sine of x is, we know that the reciprocal of hyperbolic sine is hyperbolic cosecant, so this will become hyperbolic cosecant of x dx. Okay, so similarly, we will do here what we did in deriving the integral for trigonometric function, no, of cosecant. So here, we will multiply the numerator and the denominator with, this time, hyperbolic cosecant of x plus hyperbolic cotangent of x. Okay, so similar with the derivation for the integral of cosecant. Okay, so distributing the numerator, so we have the numerator will be factoring out dx first, so we have cosecant, hyperbolic cosecant squared of x plus hyperbolic cosecant x, hyperbolic cotangent x, and then dx. Okay, in the denominator, it's cosecant, hyperbolic cosecant of x plus hyperbolic cotangent of x. Okay, so we will be using the logarithmic, no, integrals that lead to logarithmic functions. So let's review. Integral of du over u is equal to ln of u plus c. So in this case, our u is the denominator, so our u is hyperbolic cosecant x plus hyperbolic cotangent of x. So therefore, our du is equal to, so the derivative of differential of hyperbolic cosecant is negative hyperbolic cosecant of x, hyperbolic cotangent of x dx. And for the hyperbolic cotangent, it's minus hyperbolic cosecant squared x dx. Okay, so therefore, our du should be negative, factoring out negative in dx is hyperbolic cosecant x, hyperbolic cotangent of x plus hyperbolic cosecant squared of x dx. Okay, so comparing our numerator, so we have negative sign now to complete the differential, so therefore we will put there negative, and then outside the integral sign we will also put negative now to balance that out. So this will become, so since the differential is complete, no, so the numerator is the complete differential of the denominator, so from proven here, so we will have negative ln of u. So the denominator is cosecant, hyperbolic cosecant of x plus hyperbolic cotangent of x plus c. Okay, and since we know that from the laws of logarithm, so we can transfer the negative sign here as the exponent, so it will become ln of hyperbolic cosecant of x plus hyperbolic cotangent of x raised to negative 1, okay, plus c. Or we can write that as sorry, ln of one over hyperbolic cosecant x plus hyperbolic cotangent x plus c. Okay, so what we need to prove now is we need to prove that 1 over hyperbolic cosecant x plus hyperbolic cotangent x is equal to tangent of 1/2 of x, or tangent of x over 2. Okay, so but first, to make it easier, so let's express the numerator and the denominator, let's express the hyperbolic cosine, hyperbolic cosecant, and hyperbolic cotangent in terms of hyperbolic sine and hyperbolic cosine. So we'll only be rewriting the fraction, the hyperbolic functions inside. So we will have 1 over cosecant hyperbolic of x plus hyperbolic cotangent of x. So write them in terms of sines and cosines, hyperbolic sines and cosines. So it will become 1 over hyperbolic sine of x plus hyperbolic, so cotangent is hyperbolic cosine of x over hyperbolic sine of x. Okay, so 1 over. So next is we can add this, and this will become, so 1 over 1 plus hyperbolic cosine of x over hyperbolic sine of x. Okay, so from the laws of from division of fractions, so this will become 1 divided by the reciprocal of 1 multiplied by the reciprocal of the denominator. So it will become 1 over hyperbolic sine of 1 times hyperbolic sine of x over 1 plus hyperbolic cosine of x. So 1 times hyperbolic sine of x over 1 plus hyperbolic cosine of x. So therefore, we can say that 1 over hyperbolic cosecant of x plus hyperbolic cotangent of x is equal to hyperbolic sine of x over 1 plus hyperbolic cosine of x. Okay, so recall that we need to express this in terms of x over 2. Okay, hyperbolic tangent of x over 2. So we might want to use the identities, similar to the double angle identities in the trigonometric identities. So those are, so recall the hyperbolic sine of 2x is equal to hyperbolic sine of 2x is equal to 2 hyperbolic sine of x hyperbolic cosine of x. Okay, so for this one, so for the hyperbolic sine of x, it means we can also express it as hyperbolic sine of x is equal to, so notice that the angle here is 1/2 of the angle here, the value here, the function here is 1/2 of the function in here. So therefore, you can also say that hyperbolic sine of x is equal to 2 hyperbolic sine of x over 2 and hyperbolic cosine of x over 2. Okay, so for hyperbolic cosine of x, so we also have hyperbolic cosine of 2x is equal to hyperbolic cosine squared of x plus hyperbolic sine squared of x. So therefore, we can also say that the hyperbolic cosine of x is equal to hyperbolic cosine squared of x over 2, okay, plus hyperbolic sine squared of x over 2. Okay, so we can replace hyperbolic sine of x with this, and hyperbolic cosine x with this. The one, on the other hand, so we remember that hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. Okay, so similarly, if we use x over 2, so similarly, the hyperbolic cosine squared of x over 2 minus the hyperbolic sine squared of x over 2, that is also equal to 1. Okay, so substituting everything, so substitute hyperbolic sine x with this, substitute 1 with this, and then substitute hyperbolic cosine with this. So we will have, let's write first the denominator because it's longer. So we have 1 is equal to this, okay, here. So therefore 1 is equal to hyperbolic cosine squared of x over 2 minus hyperbolic sine squared of x over 2, okay, plus hyperbolic cosine, so we have this, plus hyperbolic cosine squared of x plus, x over 2 plus hyperbolic sine squared of x over 2. Okay, and then the numerator is hyperbolic sine of x, so that is 2 hyperbolic sine of x over 2 times hyperbolic cosine of x over 2. Okay, so let's simplify the denominator. So we can see that we can cancel out hyperbolic sine squared of x over 2. So what will remain is hyperbolic cosine squared of x over 2, and then adding them, so we will have 2 hyperbolic cosine squared of x over 2 in the denominator. In the numerator, we will have 2 hyperbolic sine of x over 2 hyperbolic cosine of x over 2. Okay, so as we can see, we have common terms, cancel x and cancel 1 hyperbolic cosine. Okay, so therefore what will remain is hyperbolic sine of x over 2 over hyperbolic cosine of x over 2, no? So which is equal to tangent of hyperbolic tangent of x over 2. Okay, so therefore 1 over hyperbolic cosecant x plus hyperbolic cotangent of x is also equal to hyperbolic tangent of x over 2. So therefore this is also equal to ln of hyperbolic tangent of x over 2 plus c. Okay, so as you have noticed, so in inverse trigonometric functions, so we have, in, as you can see in exponential, as you can see in hyperbolic functions, no? So there are a lot of ways for you to solve problems involving hyperbolic functions. So the first one is by direct use of the formula. The second one is by using several identities. And then the third one is by expressing the hyperbolic functions in terms of exponential functions. And then applying the applying integration, no? So it depends upon the problem, so it can be done, you know, using trial and error, no? So using those three methods. So that's all for hyperbolic functions. So thank you for watching.